Yeah, we should be live. Why am I getting feedback? Monitor off. Yeah, I don't like to hear my own voice. It's really bad. I do, however, want to monitor on another device. Check the sound as well. The delay or something. Yeah, there's about 5-10 seconds delay. We can deal with that. That should be fine. So just keep going from where we started last time. Just posting about the stream. Hopefully, we get someone to join in and actually interact. It's normally someone watching but not interacting. Not very socially, not very nice. Bum, bum, bum. Yeah, okay. The post is okay. Yeah, there's some warning in YouTube Studio. Hopefully, we can just ignore as we normally do. It's been working fine. Do however have to check the sound regularly, make sure we're using the right microphone. So we're using this Fingerspelling teaching, whatever. Hopefully, there will be a teaching tool that could train me. I don't know how to use sign language. So hopefully that will be useful for others as well. But in the meantime, we're doing this Google American Sign finger spelling recognition. This is using TensorFlow. We loaded libraries, installed everything we need. I don't know why these warnings are there. Still trying to use the TensorFlow for GPU. Having trouble with that. But it took about half an hour on a CPU. So yeah, not too bad. Using Python 3.11. Now why do we need to run this again? Yeah, it's already satisfied, so I haven't actually installed anything. Output truncated, that's okay. Yes, we need to import. It takes about 8 seconds. It's the versions that we use. Ah, right, this one. Oh, so actually, yeah, this is me trying to find the GPU. For some reason it would not recognize. I'm pretty sure I should have all the CUDA drivers installed for NVIDIA, but it will still not recognize it. I don't know what's up with that. This is some code example found by Stack. It's from Stack Overflow. So it's finding all this, found 12 different examples. I'll actually give you the source from Stack Overflow, the link and everything. GPU options, the GPU options visible devices list. That doesn't sound legit. Yeah, I don't know what's trying to do something specific there. No. That's setting a specific GPU ID import. Yeah, I don't know what's that about. I was actually trying to check this, and so I'm trying to use my GPU with TensorFlow. On a CPU, the processing took half an hour. So maybe I'll leave it as is right now. I don't have GitHub Copilot running anymore. I'm using two other tools to substitute for that, try and substitute for that. One is called Tab9 and another is Captain Stack. Now I'm using Captain Stack. You can just type in, find whatever it is you want. And in this case, TensorFlow setup GPU device. It found 12 snippets of codes from Stack Overflow. The good thing, it will give you the actual link as opposed to Copilot, which will just steal code somewhere without any acknowledgements, which is not fair play. But now I'm trying to determine which one is what. Borders, visible devices, no. It's not actually. Not sure about that one. On creating an virtual environment. I'm actually not using a virtual environment. Right, so this one can select that. We don't need this line because we already have it above somewhere. This meant to be a comment out. And it prints 0. It cannot find my GPU. It's the actual link to where this code snippet came from. So you have some explanations. But I might just leave that as is for the moment. I will try sort it out offline. So yes, we're loading this data set. We have this list of image files and their corresponding labels. The labels look like such. They have a participant ID. Someone fingerspelled these phrases, and we have the coordinates for each finger. You can see, I don't know what you can see. Can you see? Yeah, this will actually have the numbers and everything. So you'll have the coordinates X, Y, and Z. We're not using the Z coordinates, supposedly because they're not accurate. So they're stored in this Parquet files. We already did the pre-processing for this stuff. Did modify the code so it doesn't do it again, because it can take some time. we already have so it will determine if the pre-processed folder already exists, and then we'll skip some stages. It's trying to, yeah, we have the pre-processed folder, and those are TensorFlow file. So it's a .tf record files, obviously of the same data. This one should run about 10 seconds or so. Generate an animation. So this is what the data looks like. If someone is using sign language to spell out certain phrases. I don't know, why do we need to detect the pause as well? But we'll just keep it there. There's some sample code from the Kaggle competition page. With storing IDs, we're already pretty sure we already did that. So, right. So this should have been quick, yeah, because this code was actually not executed because the pre-processed folder is already there. So we're essentially skipping all that. Loading the JSON file. So that's where the ground truth data is. This one's doing some padding for it. So we did have some explanations of the code in ChatGPT. Becomes a bit sluggish and slow. I don't know if I reached some sort of limit. Alright, so this is what we were doing yesterday. Let's convert some resizing and padding, detect dominant. We're detecting the dominant hand because assumingly, again, as I said yesterday, supposedly when you sign, if so for letters, you only need one hand for spelling out words, phrases. So once one hand gets tired or something, you can then switch to the other hand. So this code will recognize which hand is actually being used or visible in the frame. Right, so this one taking the TF record, converting it into tenses. Let's just pop this into explain. Please explain. See what it says. That's what we generated a couple of days ago using GitHub Copilot. We don't have it anymore because the trial, a 1 month trial, have ended. Just read this one.
The decode_fn function is used to decode a single example stored in a TF record file. Let's break down the steps performed in the function. Define the schema. A schema is defined using a dictionary comprehension. For each feature column in feature_columns, a tf.io.varlen feature is created with type equals tf.float32. Additionally, a tf.io.fixedLength feature is defined for the phrase feature with type equals tf.string. Parse the single example. The tf.io.parse_single_example function is used to parse the record_bytes input using the defined schema. It extracts the feature values from the TF record example and returns a dictionary of tensors. Retrieve the phrase. The phrase tensor is extracted from the parsed features dictionary and assigned to the variable phrase. Process the landmarks. The landmarks data for each feature column is retrieved using tf.sparse.to_dense. This converts any sparse tensors to dense tensors. The resulting dense tensors for each feature column are collected into a list using a list comprehension. Transpose the landmarks. The collected landmarks tensors are transposed using tf.transpose. This is done to maintain the original shape of the landmarks data, where each row represents a frame and each column represents a specific landmark. Return landmarks and phrase. The transposed landmarks tensor and the phrase tensor are returned as the output of the decode_fn function. In summary, the decode_fn function takes a single example encoded as record_bytes, decodes the features using the specified schema, retrieves the phrase and landmarks data, and returns them as separate tensors. The landmarks are transposed to match the expected shape for further processing.
Right, and this one here, you get the completions by tab 9, which is kinda similar to what the Copilot does. It's, yeah, I'm still testing it. So here, for example, it's suggesting doing that. I don't know. Yeah, the annotations are not great. Yeah, it's doing something weird. Doesn't seem to have the context. So we'll try to, yesterday we'll try to do more visualization. Didn't quite work, so we might leave it for now. So here we're applying masks to the landmark coordinates. It also vectorizes the phrase corresponding to the landmark using the character to prediction index JSON file. Does ChatGPT to properly help us actually need to know what the JSON file is? Probably yes. Yeah, I remember when started using ChatGPT, you could actually, once working with JSON file, and once you actually give it, you need to actually give it the example of the file, like a segment of it or something. We can open, say if we open the JSON file in Firefox. Right, so that's the dictionary. No, that's okay. That should be pretty straightforward. We're running this one. Right, so here we're getting to training and validation. We're splitting 80-20. So 80% of the data is used for training. That's okay. We trained it already. We now actually want to use the file it generated. So we have a H5 file which we actually generated a couple days ago. It took quite some time to run this thing. Yeah, I think we can run this one. So we have the a class here. Actually should be, right. I have two classes, token embedding, landmark embedding. The token embedding layers is a combination of embedding layer, positional encoding layer. Explain this in plain English. Let's try this. Explain in plain. See what it says, encode a layer for transformer. This layer is responsible for tokenizing the input that takes three parameters: the number of vocabulary tokens, maximum sequence length.
Sequence length and number underscore hid, the hidden dimension of the embedding outputs. Inside the layer, it uses an embedding layer, self.emb, to convert the input tokens into dense embeddings. It also includes a positional encoding layer, self.pos_emb, to provide positional information to the embeddings. The call function of this layer combines the token embeddings with the positional encodings and returns the result. Landmark embedding layer. This layer is designed to process landmark inputs. It takes two parameters, number underscore hid, the hidden dimension of the convolutional layers, and max len, the maximum sequence length. It consists of three 1D convolutional layers, self.sonv1, self.sonv2, self.sonv3, with the same parameters, kernel size, stride, padding, activation. These convolutional layers are responsible for processing the landmark inputs and extracting features. Additionally, it includes a positional encoding layer, self.pos_emb, similar to the token embedding layer. The call function of this layer applies the convolutional layers to the input and returns the result. In summary, the token embedding layer handles token inputs by embedding them and adding positional encodings, while the landmark embedding layer processes landmark inputs using 1D convolutions and positional encodings. These custom layers can be used within a neural network model to incorporate token and landmark information for further processing and learning. The code defines a custom layer called transformer encoder, which represents one layer of the transformer encoder architecture. The transformer encoder is commonly used in sequence-to-sequence tasks and language modeling. In plain English, the transformer encoder layer takes several parameters: embed_dim, the dimension of the input embeddings, number_heads, the number of attention heads, feed_forward_dim, the dimension of the feed-forward network, and rate, the dropout rate. Inside the layer, the self.att component is a multi-head self-attention layer. It performs self-attention on the input sequence using multiple attention heads, with each head attending to different parts of the sequence. The key_dim parameter specifies the dimensionality of the key vectors used in attention calculations. The self.ffn component is a feed-forward network. It consists of two dense layers with activations in between. The first dense layer applies a nonlinear activation function, ReLU, to the outputs, and the second dense layer maps the outputs back to the input embedding dimension. The self.layernorm1 and self.layernorm2 components are layer normalization layers. They normalize the input by subtracting the mean and dividing by the standard deviation, applying the normalization independently to each feature. The self.dropout1 and self.dropout2 components are dropout layers. They randomly set a fraction of the input units to 0 during training, which helps prevent overfitting. In the call function, the input sequence is passed through the self-attention layer, self.att, and the resulting attention output is subjected to dropout, self.dropout1. The original input is added to the attention output and normalized using layer normalization, self.layernorm1. The output from the previous step is passed through the feed-forward network, self.ffn, and the resulting output is subjected to dropout, self.dropout2. The original input is added to the feed-forward output and normalized using layer normalization, self.layernorm2. The final output of the transformer encoder layer is the normalized sum of the original input and the feed-forward output. In summary, the transformer encoder layer applies self-attention and feed-forward operations to the input sequence, while utilizing layer normalization and dropout for regularization. This layer can be stacked multiple times to build a complete transformer encoder architecture.
to somehow visualize what it does. It was a good example of something of visualizing training of visualizing training. It was a sped up version of it, but could be a good way to proceed. It's just defining a class. It's another class.
The code defines a custom layer called transformer decoder, which represents one layer of the transformer decoder architecture. The transformer decoder is commonly used in sequence-to-sequence tasks and language modeling. In plain English, the transformer decoder layer takes several parameters: embed_dim, the dimension of the input embeddings, number_heads, the number of attention heads, feed_forward_dim, the dimension of the feed-forward network, and dropout_rate, the dropout rate. Inside the layer, the self.layerNorm1, self.layerNorm2, and self.layerNorm3 components are layer normalization layers. They normalize the input by subtracting the mean and dividing by the standard deviation, applying the normalization independently to each feature. The self.self_att component is a multi-head self-attention layer. It performs self-attention on the target sequence, allowing each position in the target sequence to attend to other positions within the target sequence. The self.enc_att component is a multi-head attention layer. It performs attention between the target sequence and the encoded output of the encoder. The self.self_dropout, self.enc_dropout, and self.ffn_dropout components are dropout layers. They randomly set a fraction of the input units to 0 during training, which helps prevent overfitting. The self.ffn component is a feed-forward network. It consists of two dense layers with activations in between. The first dense layer applies a nonlinear activation function, ReLU, to the outputs, and the second dense layer maps the outputs back to the input embedding dimension. In the call function, the causal_mask is created to mask the upper half of the dot product matrix in self-attention. This prevents flow of information from future tokens to the current token. The target sequence is passed through the self-attention layer, self.self_att, with the attention mask set to the causal_mask to prevent attending to future tokens. The original target sequence is added to the self-attention output, normalized using layer normalization, self.layerNorm1, and subjected to dropout, self.self_dropout. The resulting output is passed through the encoder-decoder attention layer, self.enc_att, with the encoded output as the key-value pairs and the target self-attention output as the query. The output from the previous step is added to the original target sequence, normalized using layer normalization, self.layerNorm2, and subjected to dropout, self.enc_dropout. The resulting output is passed through the feed-forward network, self.ffn, and the output is added to the previous output, normalized using layer normalization, self.layerNorm3, and subjected to dropout, self.ffn_dropout. The final output of the transformer decoder layer is the normalized sum of the previous output and the feed-forward output. In summary, the transformer decoder layer applies self-attention and encoder-decoder attention operations to the target sequence, while utilizing layer normalization and dropout for regularization. This layer can be stacked multiple times to build a complete transformer decoder architecture.
Right. This is where the calculation of performance using Levenstein distance. Not actually doing anything, just running within a second, just defining some things.
The code defines a custom model class called transformer, which represents the transformer architecture for sequence-to-sequence tasks. The transformer model consists of an encoder, decoder, and a classifier. In plain English, the transformer model takes several parameters such as number_hid, hidden dimension, number_head, number of attention heads, number_feed_forward, dimension of the feed-forward network, source_maxlen, maximum length of the input source sequence, target_maxlen, maximum length of the target sequence, number_layers_enc, number of layers in the encoder, number_layers_dec, number of layers in the decoder, and number_classes, number of output classes. Inside the model, the loss_metric and ACC_metric are metrics used for tracking the loss and edit distance during training. The enc_input is an instance of the landmark embedding class, which performs embedding and convolution operations on the input source sequence. The dec_input is an instance of the token embedding class, which performs embedding and positional encoding operations on the target sequence. The free sequence. The encoder is a sequential model that consists of the enc_input followed by multiple transformer encoder layers. The number of transformer encoder layers is determined by the number_layers_enc parameter. The decoder layers, transformer decoder, are dynamically added to the model based on the number_layers_dec parameter. Each decoder layer is added as an attribute to the model. The classifier is a dense layer that maps the output of the decoder to the number of output classes. In the call function, the input sources are passed through the encoder, and the output is stored in X. The decode function is called passing X, encoder output, target sequence, and training mode. The decode function performs the decoding process using the decoder layers. The output of the decode function is passed through the classifier layer, and the final output is returned. The model also implements the train_step, test_step, and generate functions for training, testing, and generating predictions, respectively. During training, the model calculates the loss, performs backpropagation, and updates the metrics, loss and edit distance. The generate function performs inference using greedy decoding, generating the target sequence token by feeding the previous token as input to the decoder. In summary, the transformer model class implements the transformer architecture for sequence-to-sequence tasks. It consists of an encoder, decoder, and a classifier, and provides methods for training, testing, and inference. Free research preview. ChatGPT may produce inaccurate. The transformer model class implements the transformer architecture for sequence-to-sequence tasks. It consists of an encoder, decoder, and a classifier, and provides methods for training, testing, and inference.
Interestingly, this code has a reference to another sample code. This, what the description of it is.
Data loading. Here I use new tokens for padding, start and end. Work is based on Rohit Injalila's notebook. If my work is helpful to you, remember to upload his notebook too. The code is essentially the same. I made some changes and fixed some problems. I used 2 transformer layer in the encoder instead of 4. I used 4 attention heads instead of 2. I used new tokens for SOS, EOS, and padding, very minor since Rohit used rare tokens for these purposes, but still more correct. I fixed a bug, probably, in the decoder's dropout layers, which did not have the training flag, resulting in dropout during inference. This change gave a nice bump in the score. I made the passing of the training flag explicit. I know it can be implicit since it is a quark, but explicit passing makes the whole thing more straightforward and maybe fix another 1 or 2 training flag related bugs along the way. I changed the positional encoding in the decoder from tf.keras.layers, embedding to proper positional embeddings, i.e., the usual signs and cosines usually used for this purpose. This had a significant impact. I added positional embedding to the encoder. This, too, had a significant impact. The rest should be very similar to Rohit's notebook.
Yeah, so this is how much it scored. How long for it to, how long takes to run. The previous one running even longer. 1,000 seconds difference. So this one displays predictions, like being able to display stuff. Just see. It will. So this is what the current model does in terms of training. So the loss function going around 0.5. So what this number is as well. Not sure. I don't think so. It's like 50-50. That's the page for the competition, by the way. That's where the data is from. Yeah, the highest score is 0.78. And this code was actually suggested in the overview. No, code requirements. Alright. This data notebook. 0.48, 0.56, and this one is quicker, but it doesn't have a score. Yeah, it sounds from this description that like when someone says I use 2 transformer layer in the decoder instead of 4, well, it would be really good if there was reasoning provided behind that. It seems, as far as I'm concerned, just a chance thing. So essentially, no reasoning behind it. So we are trying participating in the competition will be nice, but mainly we're trying to learn what all this means and how the training is performed, how it's being evaluated mainly. So this bit of code is
The code defines a custom callback class called displayOutputs that is used to display a batch of model outputs after every 4 epochs during training. The purpose of this callback is to visually compare the target sequence with the predicted sequence. In plain English, the displayOutputs callback class takes several parameters. Batch, a test batch used to obtain the source and target sequences for display. IDX_2_token, a list containing the vocabulary tokens corresponding to their indices. This is used to convert the indices in the sequences to their respective tokens. Target_start_token_IDX, the index representing the start token in the target vocabulary. Target_end_token_IDX, the index representing the end token in the target vocabulary. Inside the callback, the on_epoch_end method is executed at the end of each epoch. If the current epoch is not a multiple of 4, the method returns without performing any action. If the current epoch is a multiple of 4, the following steps are performed. The source sequence is extracted from the batch. The target sequence is extracted from the batch and converted to a NumPy array. The generate method of the model is called, passing the source sequence and the start token index for decoding. This generates the predicted sequence. The predicted sequence is converted to a NumPy array. For each sequence in the batch, the target and predicted sequences are constructed by iterating over the indices and converting them to tokens using the IDX_2_token list. The iteration stops when the end token index is encountered in the predicted sequence. The target sequence and the predicted sequence are printed to the console with appropriate formatting. The purpose of this callback is to provide a visual comparison between the target and predicted sequences, allowing for evaluation and monitoring of the model's performance during training.
right. This is like very odd. If epoch is the number of epochs, this meant to be printing something as an output. Because it's just defining a function that's not being used yet. Target text and prediction. So this is what's used to evaluate performance. And where is the Levenstein distance being calculated in this previous function? Return. Is this the distance? That's the additive distance. Compute the Levenstein distance between the sequences. So this actually getting the score. We had a simple code for testing this. It's essentially we had it in a previous stream, the previous video. But essentially, if you're making a one character mistake, then the Levenstein score will be 1. So essentially, the lower it is, the better. So if Levenstein score is 0, meaning you were able to detect, detection, predict. What are they using? Predict. Function process used to detect the dominant hand. That makes sense. It's detection. I think they're using actually predict. Those character to predict. Let's expand on this one. Without. It's okay, we can leave the link, it's just Wikipedia.
The paragraph describes the approach of using a transformer model to train a model for the ASL fingerspelling dataset. Transformers are a type of neural network architecture commonly used for processing sequential data, such as text or speech. In this case, the model architecture is inspired by the transformer model used in the automatic speech recognition (ASR) with transformer tutorial provided by Keras. Since the problem of ASL fingerspelling recognition is similar to speech recognition in terms of predicting a sentence from a sequence of data, the tutorial's transformer model can be fine-tuned for this task. Fine-tuning involves training only a small part of the pre-trained model while keeping the majority of the model's parameters fixed. By leveraging the transformer architecture, which has demonstrated success in processing sequential data, the model can learn to recognize and predict the corresponding phrases or sentences represented by the input ASL fingerspelling sequences.
Oops, sorry, my microphone was muted. That's not fun. Anyway, I'm saying we fixed that error. It was just missing beat in the code. I don't know where it disappeared into. We have this model H5 file. It's 20 megabytes. We have now 19 megabytes of model TF Lite. So I think it's the same model for TensorFlow Lite. I think actually the condition of the competition was to use TensorFlow Lite. I think that's because it's meant to be running on a mobile device. Describe the difference between TensorFlow model and TensorFlow Lite model.
TensorFlow, TensorFlow is a comprehensive deep learning framework that provides a wide range of functionalities for building, training, and deploying machine learning models. It offers a flexible and scalable architecture for developing models across various domains, including computer vision, natural language processing, and reinforcement learning. TensorFlow supports training on both CPUs and GPUs, allowing for efficient computation on different hardware setups. It provides advanced features such as automatic differentiation, distributed training, model serving, and deployment options for various platforms. TensorFlow Lite, TensorFlow Lite is a lightweight version of TensorFlow designed specifically for mobile and embedded devices. It aims to provide fast and efficient inference capabilities for running machine learning models on resource-constrained devices, such as smartphones, IoT devices, and microcontrollers. TensorFlow Lite models are optimized for low latency and low power consumption, allowing for real-time inference on edge devices. TF Lite supports various hardware accelerators, such as GPU, DSP, and neural processing units, NPUs, to maximize performance. It also provides tools for model conversion and quantization to reduce model size and improve inference speed. In summary, the main differences between TensorFlow and TensorFlow Lite are: functionality. TensorFlow offers a comprehensive set of tools and functionalities for building, training, and deploying machine learning models, while TensorFlow Lite focuses on lightweight inference specifically for mobile and embedded devices. Resource efficiency. TensorFlow Lite is optimized for resource-constrained devices, enabling efficient inference with low latency and low power consumption. TensorFlow, on the other hand, provides more flexibility and scalability but may require more computational resources. Platform support. TensorFlow supports a wide range of platforms, including CPUs, GPUs, and distributed systems. TensorFlow Lite focuses on mobile and embedded platforms, providing support for Android, iOS, Linux, microcontrollers, and other edge devices. It's important to note that TensorFlow models can be converted to TensorFlow Lite format for deployment on mobile and embedded devices, allowing developers to leverage the benefits of both frameworks based on their specific use case requirements. Regenerate response. Free resource.
Now, so we still plot this. No. Oops. Just still 20 megabytes. It's taking the code below saved model to file model saved. Um, just finish with this to explaining them quickly. Almost done with the code. We'll start coding hopefully today. If not, have another half an hour or so.
The code snippet defines a TF-like model class that extends the TF module class. This class is designed to wrap an existing model and provide a TF-like compatible interface for inference. Here's a breakdown of the code. The TF-like model class has an init method that initializes the model. It takes the main model as input and sets the target start and end token indices. The call method is decorated with the TF.function decorator and specifies an input signature for the function. This ensures that the method can be traced and optimized for TF-like conversion. The call method takes the input tensor, preprocesses it, and passes it through the main model's generate method. It retrieves the predicted sequence and performs post-processing to remove the start and end tokens. The predicted sequence is then converted to one-hot encoding using TF.1_hot. The method returns a dictionary with the output tensor named outputs. The TF-like model class can be used to create a TF-like compatible model that can be saved and deployed on resource-constrained devices using TensorFlow Lite.
Essentially the last bit.
The code snippet demonstrates the process of converting a Keras model to a TensorFlow Lite, TF Lite, model and saving it to a file. It also shows how to save the inference arguments in a JSON file. Here's an explanation of the code. The TF.lite.TF-Lite converter from _Keras_model method is used to create a TF-Lite converter from the flight model _base model. The supported _ops property of executing this code, you will have a TF-Lite model file, model.flight, and an inference arguments JSON file, inference_args.json, saved in the specified paths. These files can be used for deploying and performing inference with the TF-Lite model.
Right, we don't want to execute it for now. Inference arguments. Did we generate? Because we already generated this before. Should have the new JSON file as well. Yeah. Try to open the file with, yeah, Firefox is better. Yeah, I'm not sure what the inference arguments file is, but where did we get the first error? We want to load the model instead of running it. So the model feed. Yeah, that's starting the training process. So this whole code, I want to change it to yeah, we already had this before. Windows H a change the code, change the code to only do model fitting if model h5 file does not exist. Do only model fit if model h5 file does not exist. And then we also want to load the model instead of creating it. Let's understand what I want.
To modify the code to only perform the model fitting if the models.h5 file does not exist, you can add a check to verify if the file exists before starting the training. Here's an updated version of the code. In this modified code, a check is added using os.path.exists, model_checkpoint, to verify if the model checkpoint file, model.h5, exists. If the file doesn't exist, the model and training process will be executed as before. After training, the model will be saved using model.save, model_checkpoint. If the model checkpoint file already exists, the code will skip the model creation and training part and directly load the pre-existing model using keras.models.load_model, model_checkpoint. This way, the model will only be trained if the model checkpoint file does not exist, ensuring that training is performed only when necessary.
That's exactly right. We just modified. Just want to keep just copy the whole thing. Yeah, so if that's what the error is, it must be the folder. Can't actually find the file, is it? Yeah, are we in the correct path? No. A copy as path. Would it understand just this? Right. You just say change the checkpoint to that. Problem? This is a correct path.
Error occurs when trying to load a model from a file that does not contain the necessary configuration information. This can happen if the specified file is empty or does not contain a valid model saved using model.save. To resolve this issue, please ensure that the model.h5 file you are trying to load contains the correct model configuration and weights. If the file is empty or does not exist, you will need to train and save the model first using the code provided in the previous response. If you have already trained and saved the model, double-check the file path to ensure it is correct. You can use the os.path.exists function to verify if the file exists before attempting to load it.
and run it in terminal. I know it exists because it goes checkpoint. Do I need to train it again? Is there something wrong with that file? What? Workaround Python. Meant to be a model fit. Just execute everything above. Might take some time. Be back in a sec. Yeah, I think there's something wrong with that model file. Suspect I have to delete it.
Google, American Sign Language Fingerspelling Recognition. Train fast and accurate American Sign Language fingerspelling recognition. There's Section 11, Winners' Obligations, of the general rules below. You hereby grant and will grant competition sponsor the Visual participants and teams may use automated machine learning tools, AMLT, example, Google AutoML, H2O driverless AI, etc., to create a submission, provided that the participant or team ensures that they have an appropriate license to the AMLT such that they are able to comply with the competition rules. The following provision is added to the end of Section 11 of the general competition rules below. Individual participants and teams who create a submission using an AMLT may win a prize. However, for clarity, the potential winner submission must still meet the requirements of these rules, including but not limited to Section 8.1, Winner's License, Section B.11, Winner's Obligations, and Section B.17, Warranty, Indemnity, and Release. B. General Competition Rules. 1. Binding Agreement. To enter the competition, you must agree to these official competition rules, which incorporate by reference the provisions and content of the competition website and any specific competition rules above, collectively, the rules. Please read these rules carefully before entry to ensure you understand and agree.
But there was something about, yeah, that's true. Like all the rules. Don't like rules. But yeah, something about the training voltage. Yeah, that you have to submit the TensorFlow Lite model. So essentially, that's what the submission is, to give them the model. Anyway, it sounds like I have to run this thing again. Oops. Is that the correct file? Yes. Let's double check. It's recognizing the file. I tested somehow. Get corrupt or something. I can still see it. It's still got 20 megabytes in it. Yeah, I probably have to do training again. Now, how do we do it on the GPU? We have it in submission zip, but that would be on the TF Lite. The compression ratio is pretty good. It's like 19. Supposed to JSON file is only 86% compression rate. Yeah, sounds like I have to do it again. And the zip file, I zipped it myself because it was giving me errors as well. The code to zip. Yeah, this bit. I'll just call it the. Just change the file name. And now when running this, right, and it's using my CPU. Can't send CPU. What? Okay, let's stop this for a sec. I use the GPU for it. Use GPU. Yeah, this was deprecated. It's not correct. Yeah, this bit. Don't need that. Check GPU. But is that the same bit? It must be the GPU drivers. Pretty sure I have CUDA installed.
Utilize GPU acceleration for training a TensorFlow model. You need to ensure that you have the necessary GPU drivers installed on your system. Here are the general steps to follow. Check the GPU compatibility. Make sure your GPU is compatible with CUDA, which is a parallel computing platform and application programming interface (API) model created by NVIDIA. You can find the list of supported GPUs on the NVIDIA website. Install CUDA Toolkit. Download and install the CUDA Toolkit from the NVIDIA website. The CUDA Toolkit includes the necessary drivers and libraries to enable GPU acceleration. Verify driver installation. After installing the CUDA Toolkit, verify that the GPU drivers are correctly installed. You can usually find a driver management tool provided by NVIDIA, such as the NVIDIA Control Panel, where you can check the driver version and ensure it matches the CUDA Toolkit requirements. Install CUDNN. CUDNN, CUDA Deep Neural Network, is a GPU-accelerated library for deep neural networks. Download and install the CUDNN library from the NVIDIA developer website. Make sure to choose the version that matches your CUDA Toolkit version. Test GPU availability. To verify that TensorFlow recognizes and can use your GPU, run the following code snippet. Python. Copy code. CUDA installation guide for Microsoft Windows. The installation instructions for the CUDA Toolkit on Microsoft Windows systems. 1. Introduction. CUDA is a parallel computing platform and programming model invented by NVIDIA. It enables dramatic increases in computing performance by harnessing the power of the graphics processing unit, GPU. CUDA was developed with several design goals in mind. Provide a small set of extensions to standard programming languages, like C, that enable a straightforward implementation of parallel algorithms. With CUDA C/C++, programmers can focus on the task of parallelization of the algorithms rather than spending time on their implementation. Support heterogeneous computation where applications use both the CPU and GPU. Serial portions of applications are run on the CPU, and parallel portions are offloaded to the GPU. As such, CUDA can be incrementally applied to existing applications. The CPU and GPU are treated as separate devices that have their own memory spaces. This configuration also allows simultaneous computation on the CPU and GPU without contention for memory resources. CUDA-capable GPUs have hundreds of cores that can collectively run thousands of computing threads. These cores have shared resources including a register file and a shared memory. The on-chip shared memory allows parallel tasks running on these cores to share data without sending it over the system memory bus. This guide will show you how to install and check the correct operation of the CUDA development tools. 1.1 System Requirements. To use CUDA on your system, you will need the following installed. A CUDA-capable GPU. A supported version of Linux with a GCC compiler and toolchain. NVIDIA. Ported Microsoft Windows operating systems. Microsoft Windows 1121 H2. Microsoft Windows 1122 H2 SV2. .32-bit compilation native and cross-compilation is removed from CUDA 12.0 and later toolkit. Use the CUDA toolkit from earlier releases for 32-bit compilation. CUDA driver will continue to support running 32-bit application binaries on GeForce GPU. WS is limited. Basic instructions can be found in the Quick Start Guide. Read on for more detailed instructions. The setup of CUDA development tools on a system running the appropriate version of Windows consists of a few simple steps. Verify the system has a CUDA-capable GPU. Download the NVIDIA CUDA Toolkit. Install the NVIDIA CUDA Toolkit. Test that the installed software runs correctly and communicates with the hardware. 2.1. Verify you have a CUDA-capable GPU. You can verify that you have a CUDA-capable GPU through the Display Adapters section in the Windows Device Manager. Here you will find the vendor name and model of your graphics cards. If you have an NVIDIA card that is listed in https://tGPU is CUDA-capable. The release notes for the CUDA Toolkit also contain a list of supported products. The Windows Device Manager can be opened via the following steps. Open a Run window from the Start menu. Run. The NVIDIA CUDA Toolkit is available at https://developer.n. Platform you are using in one of the following installer formats. Network installer, a minimal installer which later downloads packages required for installation. Only the packages selected during the selection phase of the installer are downloaded. This installer is useful for users who want to minimize download time. Full installer, an installer which contains all the components of the CUDA Toolkit and does not require any further download. This installer is useful for systems which lack network access and for enterprise deployment. The CUDA Toolkit installs the CUDA driver and tools needed to create, build, and run a CUDA application as well as libraries, header files, and other resources. Download verification. The download can be verified by comparing the MD5 checksum posted at https://developer. that of the downloaded file. If either of the checksums differ, the downloaded file is corrupt and needs to be downloaded again. 2. For installing the toolkit, you should read the release notes, as they provide details on installation and software functionality. Note: the driver and toolkit must be installed for CUDA to function. If you have not installed a standalone driver, install the driver from the NVIDIA CUDA Toolkit. Note: the installation may fail if Windows Update starts after the installation has begun. Wait until Windows Update is complete and then try the installation again. Graphical installation. Install the CUDA software by executing the CUDA installer and following the on-screen prompts. Silent installation. The installer can be executed in silent mode by executing the package with the yes flag. Additional parameters can be passed which will
That might need a driver update. So I might take it offline. See you later. Bye.